Okay, guys, welcome back. We're going to be going over a cool linear algebra problem that I found, and I just wanted to share with you. And so, first of all, this is going to be about a closed form of Fibonacci sequence, and in linear algebra, of course. So, if you don't know what those are, this video might be a bit hard to understand. Okay, so first things first, let's define the Fibonacci sequence. It is defined recursively by the following: an equals an minus 1 plus an minus 2. And with the initial conditions that a0 is equal to 0, a1 is equal to 1. Okay? Some people might argue that, a0 is equal to 1, but doesn't really matter. Like, you could just shift the indexes. And and for the linear algebra part, we're going to consider this matrix: 0, 1, 1, 1. We'll give it a name A. So what is interesting about this matrix? If we were to consider, let's say, a 1 by 2 matrix, let's name it xn, and we have its entries as an and an plus 1, right? And we sub that into A. So we have A of xn, which is the same thing as 0, 1, 1, 1 times an plus 1. And what we get an and an plus, an plus 1 and an plus 1. But this is recursively defined, right? So we have an plus 1 and an plus 2, because we have an plus 1 is equal to an plus 2. So what we see here is that when we plug in x into A, we get xm plus 1. Okay, so now that we have this, what do we want to know about the closed form? Well, since we have a 2 by 2 matrix, we can use diagonalization and try and diagonalize this matrix. So what we do is that we first need to find the eigenvalues of the 2 by 2 matrix A. And to do that, let me just write it down. To do that, we need to consider A minus lambda I. And we want to find the characteristic polynomial, which will give us all of the eigenvalues. So A minus lambda I is equal to minus lambda 1, 1, 1, 1 minus lambda. I could just take the determinant, but I like to practice my Gaussian elimination. So we can switch row 1 with row 2. 1 minus lambda 1. I'll write this down somewhere here. Row 1 goes switch with row 2. And for the second row, we can cancel out the minus lambda at the bottom. 1 minus lambda, and with the algorithm, row 2 goes to row 2 plus lambda row 1. And this will be 1 plus lambda minus lambda squared. And for this, the characteristic polynomial P-char is equal to lambda squared minus lambda squared plus lambda plus 1 here, because the only way for this to have a null space, which will give us an eigenvalue, is if this is 0. Okay, so now that we have the characteristic polynomial, we can just find the eigenvalues. So the eigenvalue will be negative 1 plus minus square root of b squared minus 4ac, which is 5 over root 2, which if we take out a -1, we cancel out a -1, be 1 plus minus square root of 5 over 2. And yeah, so the eigenvalues, I'll give it, yeah, so the eigenvalues, I'll give it good names, I don't know, A and B, A is equal to 1 plus root 5 over 2, B is equal to 1 minus root 5 over 2, just to remember it better. These are the eigenvalues. And now we want to diagonalize the matrix. Okay, actually, let me change A and B, so, because they'll probably mess up with A in the future. I'll just change it to, I'll write it in red as well, alpha and beta. And now our next step is to diagonalize, as I said before. So what diagonalization means is we have A and we want to put this in a form. We want to find a matrix P such that P, D, and P inverse is A, with D is the diagonalized matrix with eigenvalues along the diagonal. And to do this, we just need to find the eigenspaces of P, which we can find by getting by utilizing these eigenvalues that we got from before. So let's do that. So let's do it with alpha first. What it means to get an eigenspace is to find the null space of alpha. So we have null of a minus alpha I, which is the same thing as minus alpha, 1, 1, 1 minus alpha, and null, forgot. And if you don't know, this is the same thing, this is equivalent to finding a 1 by 2 matrix such that 1, 1, this matrix times some matrix, call it x, y, such that that is equal to the 0 matrix. And it's not that hard, but I won't do this manually, but if you like put it into Wolfram or something, you can just find out that if you set xy as 1 and alpha, this works. That means it is spanned by this vector. Similarly, for beta, we have, well, it's the same thing, null of a minus beta I, which is equivalent to minus beta, 1, 1, and 1 minus beta times x, y is equal to 0, 0. And same thing, 1 beta works. Now that we have that, we have P, right? P is just 1 alpha, 1 beta. You just join them together and you get P. Sorry. And to find P inverse, I'm not going to do it. It's not that hard. It's a 2 by 2 matrix. You could probably do it out yourself, but I will write it out for you. I will factor out a root 5 just to make it easier in the calculations for the future calculations that we need. And this will be minus beta, alpha, 1, and minus 1. Okay, and now we're almost done because we have that A is equal to P times D times P. I'll write it out more specifically. We have that 0, 1, 1, 1 is equal to 1 alpha, 1 beta. I'll write root 5 here, times alpha, beta, zeros, and minus beta, alpha, 1, and minus 1. That is equivalent. Okay, so we're back here, and let me just write this in blue. We have AXN is equal to xn plus 1, and this implies that we have x of n is equal to a n xn minus 1. And we can do this recursively as well, where we just take a higher power and xn minus 2, right? And then it's going to be a cubed xn minus 3, and so on, until we get to an x of 0. And why do we do this? It's because remember how we defined in the beginning, the Fibonacci sequence. We have a0 equals 0 and a1 is equal to 1. So we have x0 is equal to 0, 1. And we could substitute this in here. And if we could compute what a of n is, we would get what x of n is. Then x of n has an in its, it would have an in its form, and its 1 by 2 matrix as an entry. Okay, so we want to find xn is equal to an times xo, right? And this is why we did the diagonalization, right? Because if we take any power of the diagonalized matrix, this will just be equivalent to taking the powers of the eigenvalues inside. And so let's just compute it. So xn is equal to instead of writing a to the power of n, we're going to write the diagonalized matrix, 1 over root 5, 1 alpha, 1 beta, times alpha 0, beta 0 to the n, respectively, and minus beta alpha 1 minus 1. And then we can just multiply, I guess. 1 over root 5. This is going to be alpha to the n, alpha n plus 1, beta n, beta to the n plus 1. Oh, I forgot. This is going to be x0, which is the same thing as 0, 1, because that's how we define xo. And times b alpha 1 minus 1, 0, 1. Yeah, you can see them clearly really slow at computing stuff. Alpha minus alpha and beta plus beta and alpha. And this is alpha n minus beta n, alpha n plus 1, beta n plus 1 times 0, 1. And 1 over root 5 alpha n minus beta n, alpha n plus 1, minus beta n plus 1 after multiplying it out. And this is what we want, right? This is equal to an plus 1. And since we only care about the an term, as that's what we want, we can just we can only care about this, and we take that an is equal to 1 over root 5 times alpha n minus beta n. And I'll just write it out because you might have forgotten what it means. 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. And we're done. This is the closed form of the Fibonacci sequence using linear algebra. And